Hey, g'day and welcome to the Prezo Show. This is my workshop. This is where I do my thing, and it's all about making and learning. Now I wanted to share with you today this beautiful 3D printed sticker that was sent to me by a gentleman named Steve Smith who lives in Filton in the UK. And I reckon that all you guys are doing these 2D stickers, that's so 2020. Should really be getting onto these 3D printed ones. Now, what's the story with this? Okay, now I did a small job for Steve recently, and in return he sent me this beautiful CNC machined bottle opener, complete with my logo on one side. Now I don't know how he got that, or actually I do know, he pinched it off one of my videos and he drew around the edges of that logo with a tool in Fusion 360 to create a vector file, and then he drag and grade that on that bottle opener. And I tell you what, I'm taking this to the next barbecue I go to, and nothing says beer snob like your own customized bottle opener. And let's face it, import beers don't have anything as pedestrian as a screw cap, do they? Now, today's video is all about finishing off the power drawbar for the Bridgeport mill. And just by coincidence, Steve is also making a power drawbar for his Chevalier mill. Now the Chevalier is the Taiwanese equivalent of the Bridgeport. It's actually a Bridgeport clone. And Steve's building this beautiful power drawbar for his mill, and you can check it out on his Instagram page, and I'll put his Instagram handle in the link below. And if you want to see some truly astounding work, check out Steve's Instagram page. He actually goes by the name SGS Engineering. So in today's video you're going to see me making making the remainder of the parts for the Mark II version of the power drawbar upgrade. And this became necessary because it wasn't self-ejecting the tools. I've actually got it working now, so we're going to see some of the parts being made and then we'll check it out working right at the end. So sit back and enjoy. To make this modification work, I've got to turn this 16mm shafting down to a diameter of 10 and 10mm back to the shoulder, and that's going to fit into this 10mm reamed hole I've already put in this bridge piece. Now the only problem is that this shafting is super hard, and the hardness extends in for at least 3mm from that 16mm diameter. So even with this insert, it's a bit of a struggle. But we'll do the best we can here. So I'm going to face this off, set the DRO to 0, see if I can turn this back to 10mm and get underneath that hardened coating on the outside there. Yeah, that's that's pretty impressive. Why don't I just zoom you in and show you how deep that coating goes. So I'd be thinking that that hardened zone is at least 3mm deep, and we've got to get completely under that, and I had to lock the carriage in order to get that faced off there so the tool wasn't going to get pushed away. Anyway, let's see if we can get this 10mm, and even when I come out to there I can feel that the tool has deflected and it's not really cut that evenly, but we've got to get under that coating anyway. Man, that's ugly. Alright, we're about 11.59 now, and I think we're pretty much inside that hardened zone. Yeah, alright, so from now on should be a bit easier. And that's now cleaning up quite well. Only problem is, just looking at my DRO, it looks like the stock has actually moved back inside the chuck here, so the pressure of turning that has moved the stock, so I'm going to need to clean up the shoulder and probably face that again to make sure I've got exactly 10mm length on that shoulder. I'm just going to swap out to my normal high-speed steel tool here now that we've got under the hardened zone. Yeah, doesn't like that hardened stuff. It's exactly size on size there, but I think we need a couple of thou clearance. That's it. Okay, let's go drill and tap this now M6. There's that part now. It's been sandblasted to get rid of all the black scale, and it's now ready for powder coat. And if you're looking at this part and saying, well, I don't get it, what's the big deal? It's just a piece of steel bar with some holes drilled in it and rounded ends. A couple of things were really important here. These two drilled holes had to be exactly 90mm apart, and a very close fit on the 10mm spigots on the end of the vertical bars. And I wanted these radii on the ends to look accurate. I reckon nothing looks worse than a rounded end that's got a flat spot or a bulge. And the technique I showed you there was one that I saw on Dale Derry's YouTube channel. So he runs the channel called Metal Tips and Tricks, saw that technique and I thought that's brilliant, because I don't have a big rotary table, and to get a nice accurate radius like that is well, I think it's actually quicker to do than to put a rotary table on the machine, center it, get all the jobs set up and so on. And well, I think the results speak for themselves. So let's go ahead now and get this powder coated. Now I've brushed the head a bit and I've done all of the powder coating for the parts for this build. Here's the bridge piece now powder coated in satin black, and I've done the base casting and the carriage casting here in a silver powder coat. And these are the original columns that I built for the Mark I version, and here are the new ones that we've turned with the spigot on the end and the thread in the end of that spigot. And you can see that there's a difference in the height, and our bridge piece will fit on top of that. And you can use socket head screws. I'm just using hex head bolts and washers to hold all that together. So that's probably the major change between the Mark I and the Mark II version. Now I've gone ahead and made some other parts here off camera because they're pretty basic sort of parts. So this is the little lever which operates the latch mechanism, and this is the stop collar. It's got two socket head grub screws in it to lock it to one of these two columns, depending on which version you make, the left hand or the right hand version. So they're just basic turning. This collar's made of aluminium. Little handle here is made of stainless steel, 7mm diameter with an M6 thread on either end. So I'm just going to put those aside for now. Now the one remaining part to be made is the actual latch mechanism, and it's going to fit onto, once again, one of these two columns, and it's going to rotate around that column. This particular latch mechanism here could be a casting, it can be a fabrication. You can machine it all out of one piece of material. I don't have a piece of stock big enough, so I'm using two separate parts, and that's going to be eventually joined together using either a press fit or Loctite or something like that. But let's go ahead and get this part made now, and it's the final piece of the puzzle, and then we'll see if we're going to be successful or not. There's that part almost done. I just need to machine this diameter here, which is not critical, but that's a piece of that 16mm rod sliding inside that, and it's a nice fit. This is where the cam or the latch is going to be mounted later on. I think we're just going to stick that on with some Loctite, maybe put a pin in it. But yeah, we'll get this cleaned up, get it the right length, then we can make the latch. I've got to get an overall length of 44mm on this part here, and I'm not even going to try to part that off, not with that grip in the chuck. So I'm just going to do it old school and just face all of that off. So we've got about, what's it, about 7mm to come off. That's alright, plenty of time. I'm done with all of the lathe work on this part now, and I need to drill the 2 holes that'll be the stop pins to limit the travel of this part. And I'm using 3/32 roll pins. I thought I had 3mm ones, but I don't. And I've set up this 16mm pin over that hole, and I've set my DRO to 0 on that position. And then the 2 holes are drilled left and right of the spindle and back in the Y direction. So on my drawing here, I've got the dimensions for those 2 holes, and I've set those positions in the DRO, so I'll go ahead and drill them now. Got those 2 roll pins in there now, and we need to be able to set this up using those pins as our reference. And I've got this resting on a parallel at the back of the device, and we'll just gently tighten that up, get everything aligned. And we can now find the center of this diameter here, offset from this shoulder, and drill and tap for M6. I had a bit of a senior moment there, and I forgot to press record on the camera, but I just did all that center finding with my wiggler, and I've just drilled 5mm there. Go ahead and tap that M6. Didn't miss much. Alright, that's pretty good. I'll just go ahead now and machine up the latch itself, which will be Loctited onto this spigot. This is my piece of 10mm thick aluminium stock. It needs to have a 19mm hole bored in one end to take that 19mm projection there. That'll be Loctited in place later. And I'm going to mark this out. Now, I bought myself one of these little marking gauges, so I saw this on Myford Boy's channel. And I thought, this is a tool that's specifically designed for marking out on material, as opposed to going and getting your beautiful Mitutoyo caliper and using that to scratch metal. That drives me insane. So I've set this to the radius of the round on the end of the stock here, and we're just going to scribe a center line there. And we'll come off our good edge, our reference edge. Okay, that's our center, and we'll center punch that and get on the lathe and bore that out to 19. Okay, to the lathe. This is still my preferred method for dialing in a part in a 4-jaw chuck, and it's not like we have to be super duper accurate here. That's close enough for me. Alright, this is interesting. Now, a while back I watched a video by Stefan Gotchwinter, and he was talking about taking balanced cuts to reach a desired dimension on a part. Now, I'm shooting for 19.01 here. I set my calipers to that dimension, and I've got the DRO set as well. And I've just been checking the measurement as I take the first of two final cuts. And I'm right on 1.1. I started at 2.2. The cut I just dialed in was 1.1. Now I'm going to take the next cut, and hopefully we don't have to take a spring pass. Now I know this boring tool will be deflecting, but it doesn't matter. If you take a cut, measure the difference, know how much it cuts, and then dial it in for the last cut, you should be able to reach your target. I know, brave words. Let's see how we go. So we're going to come back. Did I set that cut? Talking too much. Alright, so I'm going to come back to 0. Well, will you look at that? It's right on. Yeah, I was hoping that I could use Loctite in here. But that's not bad actually. I'm probably about 0.01 undersize, maybe 0.02. But that's not bad considering that we're not bothering to take a spring pass. It was just like two balanced cuts to finish off the bore. And if I take a spring pass now, I'm almost certainly going to overshoot and make that hole too large. Well, there's our latch nearly done. Just got some milling to do on here now, and we'll get this Loctited on. Just put a bit of round stock in that bored hole there. I'm going to use the same method to radius the ends of this aluminium stock here that I used to do the bridge piece. So I'm just going to grip that in the vise, keep rolling that over and taking tangential cuts. And I need to put a slope or like a taper on this as well. I think I'll rough that out first. Now I won't show you all of this, it's just a lot of repetitive machining. We'll do a quick montage and then we're going to come back, and I've got a painful admission to make. There's that part, and it needs to have a little bit of a radius on these sharp corners here, and I'll give that a deburr and clean up. Now, grab a box of tissues and I'll meet you over the bench, and we're going to talk about something sad. Well, get ready for some tears. Now, this is true confession time. And you know how you have one of those days in the workshop when everything goes right. You hit all your numbers, all your parts are good fits, you don't break any tools. Well, that's how it went with this part. And I figured I'd put it up on top of the Bridgeport head and attach it to the power drawbar and see how it all worked. And then this happened. Come on, who's responsible for this nonsense? What a debacle. And boom, just like that, he shows you the modified part. Now this is a modified part. I didn't have to make a new one, I just shortened it. The latch section now has been bonded on with Loctite. We've got a new steel handle that extends down the side of the actual column, and that places the ball handle in an easy to reach position standing in front of the machine. If I'd left this as I'd originally designed it, the handle would have been up much higher and it was uncomfortable to reach. Now this extended handle here is made of steel. It's 12 millimeters wide, 5mm thick. It's been powder coated in satin black like some of the other parts, and this now does actually work. I've tried it out and it's fine. Now what went wrong? Well, I don't know. I had originally measured the height of the cylindrical section here at 44, it should have been 22, and I made a number of assumptions, and one of those was that the drawbar was fully extended into its top position, and that wasn't the case. That could have led to this error that we're seeing here. And I can always use the universal excuse, the sun was in my eyes. Now, I've corrected the drawings, and as you can see here, this is the modified part, and I'm going to make sure that all of these drawings are up to date, and I will make sure that there are no bugs left in this. Anyway, let's go and put this together now and see it operating, and it does work, by the way, guarantee it. Well, here it is, all assembled, ready to put this back up on the head of the Bridgeport, but before I do that, I want to mention this system that I developed in the last video for increasing the resistance of this operating handle. And in the previous video I'd used a piece of this 10mm square rubber. The one that I fitted eventually didn't have the cutout, and that worked great for about 24 hours. And then what happened was this rubber just took on a set and sort of compressed and then became loose again. So I swapped that out, and what I'm using now is a piece of this spring steel. So this is a recoil starter spring, probably from a lawnmower or something like that, and it's 12.6 millimeters wide and about 0.6 of a millimeter thick, and I bent that to bear against the body of the impact wrench. So don't know if you can see it, it's just in here, and it's sort of pushed against the side of the body of the impact wrench, and that provides the resistance. Now, I'll put all the details of that spring in the 2D drawings, and if you want to replicate that, you just got to find a piece of spring steel about that size, and it's relatively easy to make. Well, there it is, fitted back up on top of the mill, and you can see now that I can reach both of these controls fairly easily. Now, you could possibly extend this handle down lower, but the operation now is in two parts. So you pull the whole mechanism down to engage the socket on the hex of the drawbar, and then slide this lever across. That locks the motor in the down position, so that when I operate this now, the thread will drive the taper of the tool out of the spindle. So just to demonstrate how this works, I've got a tool in the spindle which I know was not ejecting by itself before. I've got a sort of a basket with some cloth there, so when it does fall out, it's not going to roll on the table or on my foot. So all I should need to do now is to engage the motor, and it fell out. So I'm trying to figure out how I can show you both these things at once. Let's put it back up again. And let me zoom you in on the table itself, and we can see what's happening there. Alright, so here's my catching system that we're using, and like no hands, alright? And back up again. Now when you're finished with that, you just simply rotate that lever, and the whole mechanism springs back up to its full height, so it's now disengaged from the drawbar. So let's see it from the top. And back up. And there it is. So yes, it's a two-handed operation, which I know is going to sadden a lot of people, but it's simple and it's effective and it works. Alrighty, well that's it for me today. Thanks for joining me. In the next video we're going to be making an interesting tool for operating a Kurt style vise on a milling machine. And if you've got one of these, you've probably got the same problem I have. and I've just finished making a tool and I've got the video almost done, so it should be out in about a week. Now remember, you can get the STL files for the patterns that I use to make these castings for this device, and you can also get the 2D drawings, and the links for those are in the description below. So help yourself, they're free to use. And for now, I'm going to say thanks for watching, and I'll catch you on the next video. It's Prezzo signing out.